All right, let's talk about how one single idea from one research paper back in 2017 completely tore up the rulebook for artificial intelligence. It's the foundation for pretty much every major AI breakthrough you see today, and we're going to unpack how it all happened. This one image really says it all. On the left, that's the old way. AI processing things one step at a time, like links in a chain. It worked, but it was slow and really limited. And on the right, that's the new way, a massive interconnected web where everything can be looked at all at once. So how did we get from that simple chain to this powerful web? Well, that's exactly what we're going to get into.
To really get why this change was such a huge deal, we first have to go back and understand the world of AI before 2017. There was a fundamental problem, a wall that everyone was hitting.
For a long time, the main players in the game were called recurrent neural networks, or RNNs, and their whole idea was to process language sequentially. They'd read the first word, think about it, pass that thought on to the next step, read the second word, and so on, all the way down the line. This chain-like process was their defining feature, and, as it turns out, their biggest weakness.
This one-word-at-a-time approach created two massive roadblocks. First, what's called the long-range dependency problem. If you give an RNN a really long paragraph, by the time it gets to the end, it's pretty much forgotten what was at the beginning. The context just fizzles out down the chain. Second, the parallelization problem. Because you had to process word 1 before word 2, you couldn't throw the power of modern computers at it. It was like a line of dominoes that had to fall one by one. This made training these models incredibly, painfully slow. AI was well and truly stuck. And that brings us to the moment everything changed. The moment a small group of researchers basically said, hey, what if we're all thinking about this the wrong way?
In 2017, this paper drops. Attention is all you need. And just look at that citation count, over 173,000. In the world of academic research, that number is absolutely astronomical. It tells you just how foundational this single piece of work became. It was proposing a completely new way to think about things. The core idea was radical, almost heresy at the time. The authors suggested throwing out the entire sequential chain, that whole one domino after another thing that everyone thought was essential. They argued that a mechanism called attention, all by itself, could do the job, and do it better. This went against everything people thought they knew.
So what is this attention thing? What is this magical concept that allowed them to completely break the chain? Let's get into the weeds a little and see how this elegant solution actually works.
Okay, the key concept is called self-attention. So instead of passing information down a line, self-attention lets every single word in a sentence look directly at every other word, all at the same time. So for a word like fox, it can instantly see how much it relates to jumps and dog and quick all at once. This is that leap from the slow chain to the super-fast dynamic web.
Now, to make this work, the model uses three concepts: a query, a key, and a value. And honestly, the best way to wrap your head around this is with a database analogy. The query, or Q, is like your search term. It's the word that's doing the looking. The keys, or Ks, are like the labels on all the other words. And the values, the Vs, are the actual stuff, the substance of those words. So here's how that all comes together. First, the query for one word compares itself to the key of every other word, and that gives it a score. A higher score means they're more related. Second, these scores are turned into weights, which basically tells the model how much attention to pay to each of those other words. And third, you just add up the values of all the words, guided by those weights. And what you get at the end is a brand new version of your original word, now supercharged with context from the entire sentence.
But it gets even cleverer. The model doesn't just do this once. It uses something called multi-head attention. Think of it like having a whole team of experts look at the sentence at the same time. One attention head might be an expert in grammar, looking at how verbs and nouns connect. Another might be an expert in meaning. They all do their own analysis in parallel, and then they combine their findings for this incredibly rich, multi-layered understanding of the sentence.
Okay, this all sounds amazing, but it creates a pretty obvious new problem, right? If every word is looking at every other word at the exact same time and there's no chain, how on earth does the model know that the dog chased the cat is different from the cat chased the dog? How does it know the word order? The solution is this just beautiful, ingenious mathematical trick called positional encoding.
Before any of the attention stuff happens, the model adds a unique numerical fingerprint to each word that tells it exactly where it is in the sentence. It's like stamping each word with its own GPS coordinates. So the order isn't in the process anymore. It's baked right into the data itself. Just brilliant.
So you take all these pieces, the self-attention, the multiple heads, the positional encoding, and you put them together. The result is the transformer. And now we can see how it just completely bulldozed those two big problems that were holding AI back.
So how did this new architecture stack up? Well, that long-range dependency problem? Solved. Because every word has a direct hotline to every other word. The context doesn't fade. And the parallelization problem? Totally obliterated. Since there's no sequential chain, you can do all the calculations at the same time, which is exactly what modern computer chips are designed for.
And here is the proof. The original big transformer model from the paper was trained in just 3.5 days. 3.5 days. This didn't just beat the best models of the time. It absolutely crushed them. Models that had taken ages to develop and train. This was the moment everyone realized the entire game had changed. Forever. The shockwaves from this went far beyond just one experiment. This architecture became the blueprint, the DNA for almost everything that came next, creating a direct family line to the AI tools that are all around us today.
I mean, you can literally draw a straight line from that 2017 paper to today. In 2018, you get BERT, which completely changed how machines understand language and is now a core part of Google search. Then, of course, you have the GPT series, which focused on generating language and led straight to ChatGPT. All of them, they're all direct descendants.
And what's really wild is that the idea was so powerful it broke out of just handling text. Researchers realized they could use it for, well, anything. The vision transformer treats little patches of an image just like words. OpenAI's Whisper uses it to transcribe audio with incredible accuracy. And of course, generative AI tools like DALL-E and Sora, yep, transformers are the engine under the hood.
This quote really just nails it. The transformer isn't just another cool model. It has become the fundamental, flexible, scalable workhorse for building pretty much any kind of intelligent system you can think of. So, the story of the transformer is really about identifying and shattering a fundamental bottleneck. That slow, sequential way of thinking. And it leaves us with a pretty big question, right? What is the bottleneck holding AI back today? And what radical, counterintuitive idea is going to be the one to break it?